Right, good morning everyone. Great to have you here for another Wednesday webinar. This time around we've got Graham Hendra, who will be talking about his knowledge on air source heat pumps and retrofits, and he'll be sharing his experience of his own retrofit on his house. Graham is an independent heat pump consultant, so comes with a wealth of knowledge. Before we get going, I just want to go over some housekeeping. Please keep your microphones on mute throughout the presentation. Please ask questions through the chat box. The webinar is being recorded and will appear on our YouTube channel afterwards. As a lot of you will know, we're working really hard to develop Meshwork into a collaborative environment. The platform is completely free and we're encouraging all our members to learn from one another, share ideas and push sustainable design forward. We've got an exciting few months coming up. We've decided to develop monthly themes starting in September with health and well-being. We'll still have webinars, but we've also got interviews, case studies, really interactive questions and great content. So please feel free to join in the conversation and share Meshwork to others who may really benefit from it. And then finally, for those of you who aren't familiar with what Mesh Energy do, we're an independent and holistic energy consultancy. We're based in Surrey, but we work across the UK and globally. We primarily work with design teams and architects to make the sustainable design process as cost effective and as simple as possible. But that's enough from me. I will now let Graham share his screen and get on with his amazing presentation.
So here we go. So morning everybody. My name's Graham Hendra. I'm just trying to share. There we go. So Mesh Energy very kindly asked me to talk to you today a little bit about retrofitting heat pumps into old properties. So I'll keep this bit brief. Who am I? My name's Graham Hendra. I'm an enthusiast of heat pumps. I've been working in this sector, mostly air source, but a little bit of ground source for about 15 years. Essentially designing systems for customers, lots of fault diagnosis, and selling heat pumps into the UK market. So basically, I like to think of myself as somebody you can come to and ask silly questions about heat pumps, and hopefully I can give you fairly useful advice. So here we go. This is my experience of heat pumps in retrofits. So the big question we always get asked, and if you go on Google and type in, do heat pumps work in old houses? Lots and lots of people will tell you old houses don't work in heat pumps only work in new build, etc., etc. And to some extent, that's kind of true. New build's really easy. You have a new building, you have essentially a blank canvas. So designing a heat pump system to work on new underfloor heating, new radiators and so on is a piece of cake because you're designing everything from scratch. So kind of in a way, new build is really, really easy to do and it's not very exciting for me. I prefer to look at the challenge of old houses because there's quite a lot of them. And there are a few myths about old properties that I want to sort of look at and explain why I don't think they're true. But the first thing I think that we need to sort of get clear in heat pumps is all that really matters is that you do a really thorough survey of the property that you're going to put this technology in and carry out a heat loss calculation to make sure that the machine that you're offering to your client or to your homeowner or buying yourself is the right one and is the best solution. The problem with that is that doing the survey is quite expensive, it takes a bit of time and so on. And our feeling is that out in the market, Mrs. Miggins and the other customers out there really don't have any idea how much this technology is really going to cost and whether it's going to save them any money and so on. So what I like to do when somebody rings me and says, I think I want a heat pump, is say, well, let me just do a 5-minute couple of questions and give you some numbers and budgets before we go ahead and actually get in the car and come round with the tape measure. And to make that easy, I've built a little tool which I use every day, and I'm going to share some of it with you today and show you how it works. So the first thing I want to do is, based on a quick phone call, I'd like to get some idea of the heat load of your house. And essentially what I've put together here, you can see this little table. It's a very, very rough guide, but based on the age of your house down this axis and the size of your house on this axis, we can get a rough idea of how many kilowatts we need to pour into your house to keep it warm. So in this example, I'm going to focus on a kind of 1980s, 200 meters square, that's a sort of 4-bedroom house. And I'm going to assume a couple of things to begin with. So you can see in yellow here that if you have this 1980s house and you haven't improved it at all since the day it was built, we would expect a heat load of something of the order of 14 kilowatts in that building. Of course, if you've put a bit of cavity wall insulation, maybe improved the roof insulation and so on, that heat load will drop, and sometimes we can drop it down to the next section. So if you'd spent a bit of money on the house over the years, maybe the heat loss would still be around about 13 kilowatts. Now, before anyone jumps in and says, I've had a heat loss done on my house and it was only 9 kilowatts, you need to bear in mind this is very, very budget based on just a quick conversation. But one of the things I like to look at, as I'm a bit of a heat pump geek, is the different colors on this table are there for a reason. So the bits that are in black are the bits that are easy to do. So these houses down at the bottom here are easy to do. The ones in red are where stuff starts getting a little bit more interesting and more difficult to do. And once we get up to the blue section, it's considerably more difficult. And that's for one reason and one reason only. The biggest heat pump you can buy for a domestic property in the UK is rated at 16 kilowatts on the tin. The reason for this is that the power supply is such that if you go bigger than 16 kilowatts, you need a kind of commercial power supply. So if you look at these grey areas in the really big houses or the badly insulated houses, although it's possible to heat them with a heat pump, power supply can be an issue. So this is the area I kind of avoid, if you will. The reason that for the blue section down the middle here is that this is where we start breaking into the second heat pump. So maybe one heat pump isn't enough, 2 would be needed. So although it's very interesting for us to work out that this property has got a 13 kilowatt heat load, it doesn't really mean anything to the homeowner. One of the things that we get asked a lot is, if I have a 13 kilowatt heat load in my property, surely I should buy a 13 kilowatt heat pump. But unfortunately, due to a technicality in the way that heat pumps are sized, the number written on the side of the unit bears almost no relevance to the number of kilowatts it gives out. So as a rule, 16 kilowatt heat pump, you'll be lucky to squeeze 13 kilowatts out of it. Contrary to what manufacturers tell you, as a rule, knock a couple of kilowatts off and you won't be a million miles away. So heat pumps generally look like they're oversized, but actually they're not. Okay, so we've got our rough guideline. We think we need something of the order of 13 kilowatts in this house. Let's look at a few other bits of info. So what I've done here is a prediction of the run cost in this property. Now, one of the things that we run into is a bit of an issue is when we are doing a run cost simulation for a heat pump, we assume that you're going to run this machine 24 hours a day at 21 degrees C and heat every single room of the house all the time. So this assumes that you're not going to turn the thing on and off during the day or set it back or anything like that. It gives a really, really good guide to what would happen if you left the machine running all the time, which is the best way to heat a house with this technology. So I compare this with doing the same thing using your fossil fuel boiler. So we quite often get people saying, oh, I only heat the house 4 hours a day, so my run cost is a lot less than you predicted. But we need to set a benchmark. So we compare running a gas boiler or oil boiler or LPG, insert fuel name here, and we give you the savings. So this is something that you can see here, that based on this calculation, I can save you something of the order of £500 per year if we take a boiler which is something like 10 years old and change it for a heat pump. And this comes as a bit of a surprise to people, because they think that they're going to save enormous amounts of money with a heat pump, but that just isn't true, I'm afraid. I know it's a very unpopular thing to say, but if you are going from normal gas over to a heat pump, if you can realize a 15 to 20% saving, you're doing pretty well. Of course, if you're running against oil, the savings can be quite significant, especially when oil is costing in the high 50s and 60 pence per litre. So this calculator, I have a little tool in the background, and I can actually stick in your energy figures and give you a much more realistic figure if you know how much you pay for your gas and electricity. But 15 to 20% is quite realistic. So first thing is, we've got £500 a month, and we're going to stick that in the bank as part of our saving. The next thing that we need to talk about is grants. So like many renewables, there is a grant from the government. It's called the RHI, or Renewable Heat Initiative. And essentially what happens is the government will pay you a grant for 7 years from the date of installation. It's done automatically by direct debit, and you get a quarterly direct debit into your bank with this sum of money. So the customers generally want to know kind of how much money is that. So if we look in this table here, you can see that this property we're looking at in the green and yellow, they would expect to see something of the order of £1,550, £1,560 a year coming back, which if you times by 7 years comes up with £11,000. So they're going to get £11,000 saving from the government for the RHI. Now, there is a lot of talk out there in the internet about RHI and what's going to happen to it. And I thought I'd clear a few things up and give you the kind of sad truth of where we really are. So in March of next year, the RHI is being reviewed. There's been a lot of consultation over the last couple of years. And what I can tell you with certainty is nobody knows what the RHI will be in March of next year. Those figures haven't been released, but there's an enormous amount of speculation. However, if you talk to people in the industry who've been involved in this, there is one sort of general consensus, which is nobody believes the RHI is going up. Everyone thinks it will stay the same or fall. So it might have quite an impact on the industry, and I can honestly say that our industry is looking at this a little bit like solar. We're expecting a little bit of a boom in the springtime of next year as people rush to try and get onto this scheme if they think that the grant is going to fall. But if you find people out there telling you the RHI is going to be £5,000 a year or £10,000 or whatever, unfortunately at this stage that is pure myth. Nobody actually knows. As soon as that information is available, trust us, we will get that information out to everybody. You'll see a lot of discussion about it. So very quickly then, I'm on this house, I'm going to save about £500 a year in run cost. I'm going to add that to my £1,500 RHI per year. So I've got £2,000 per year tucked away in the bank. Now, that sort of part of the presentation I talked about there was very, very much the core of how we sold heat pumps for the last sort of few years. But in the last couple of years, and definitely in the last year or so, there's been an enormous amount of discussion about carbon. And you can see it in the news this week. There's lots of information about this. And we are seeing a bit of a change where homeowners are becoming really, really aware that they need to do their bit. So something we started doing a few years ago was saying to people, how much carbon will you save if you jump on this technology? What, you know, how much will this impact you? So again, if we look at the little table here, you can see that the units we're looking at are in here. So by moving from your gas boiler into a heat pump, we can save you something of the order of 5 tons of CO2 per year, which is pretty impressive considering that the average UK citizen emits 9 tons per per year. So it's kind of like one of you in the house is halving your CO2 output, which I think is a really, really good and positive step. One of the things we always say to people is putting a heat pump in the house does not make you carbon neutral, but it is a really, really healthy step towards that goal. We can't solve all your problems for you, but we can set you in the right direction. For those people who are really into this kind of calculation, what is really nice to think and gives you a lovely warm and fuzzy feeling is as the grid becomes more and more and more efficient and the carbon intensity of electricity falls, this figure rises. So every morning you wake up saying, I've saved just a little bit more carbon than I did yesterday, and I didn't have to do anything about it whatsoever. As other people buy renewables and put them in, you become more and more and more efficient, which is a really nice thing to do. You do get something for nothing, I guess. Okay. So I guess the really big thing that people want to know before they actually purchase one of these bits of kit or drag us in to do the survey is what kind of return on investment are we going to get? So this is quite an interesting calculation, so bear with me just for a second. If I take the saving from the gas bill, so £500 a year, plus my grant, £1,500 a year, I'm saving something like £2,000 a year. Over the 7 years, that puts me with a saving of £14,000. But one of the things that is often forgotten in our sector is people are generally only looking to invest in this technology because their existing heating system is coming to the end of its life. So the choices really are, do I spend £3,000 on a new boiler, or do I spend £13,000, £14,000 on a heat pump? Nobody tends to buy a heat pump if they've got a beautiful, perfectly working and brand new boiler. So what we do when we're doing the return on investment is we knock the cost of the boiler off the cost of the heat pump installation and just work out the ROI on the increase. And you can see here, it comes up with some really interesting figures. So in the house I've been talking about during this presentation, you get a saving of between sort of 4.5 and 7 years. And the reason for the big jump is if they don't insulate the house, and they have this higher heat load that we showed a few slides before, it puts us into a much more expensive machine, which is more expensive to install. So this is a really, really nice way of saying to the consumer, look, if we can spend a bit of money on cavity wall insulation, maybe improve the windows, maybe put some loft insulation in and get you down into the cheaper range of units, your ROI is miles quicker. So it really, really does say that insulation plus heat pumps together is a really, really good combination. Sticking a really efficient heating system into an appalling house is not possibly the best thing to do. Now, you will notice up in the top section here, the houses I talked about that are difficult to do. I didn't bother working out the return on investment. And the reason I didn't do this is it's 10, 12, 13 years and so on. And that puts a lot of people off. So I tend to avoid those areas, or we tend to discuss with people a lot more detail about they do know that they're not going to get their money back quickly. And that's where you find out who the guys are who are really interested in carbon instead of money. And the number of people who are like that are really, really increasing, which is a really positive thing. So once we've got to the base of this and we send you this very, very quick report saying this is where we are, this is your house, what do you think? Essentially, all we're trying to establish with these three little tables is the homeowner prepared to go ahead and spend the kind of money we're talking about, and are they, interested in this kind of payback? And this weeds out the people who think that heat pumps are free, or think that they're going to make an enormous saving and get sackfuls of cash delivered by the government. And so really we use this as a very, very rough guide to establish, is it worth me jumping in the car, or you jumping in the car, going to their house and completing a full survey? So it's a nice little simple tool. It works a treat. There are others online. You can see some apps and so on. I just like the little table. For me, it makes my life very, very easy. Okay. So once we've all agreed that we're in the right ballpark and a survey is a good idea, somebody will turn up at your house. That may be your installer. It could be me even. but somebody will come along and they need to come to your house and measure up the building. Essentially, what we need to leave the building with is some kind of floor plan with a scale on it, showing every room. We need to show what the walls are made of. We need to show what the windows, the floor, the ceiling, and so on. Now, this is quite an interesting thing. If you ask a homeowner what their walls are made of, they tend to say bricks, which is wonderful, but we need a little bit more information than that. So we need to actually get in the loft, have a look down the cavities, see if they are filled, measure the thickness of the walls, the inner and the outer, actually check the loft insulation is in place and how thick it is, check that the double glazing is in good condition, or the single glazing if that's what they've got, and have a really good look round. But also you'll notice a picture of a radiator up here. What I need to do is look at your radiators. I need to see how big they are, how wide, how high, whether they're singles, doubles, and so on. And one of the key things, is a real buzzy thing in our industry at the moment, is the pipe work. There is a myth out there that you cannot use a heat pump using microbore pipework. It is complete rubbish. It is harder to use microbore, and we have to be much more careful about how the system's tubed up, because the problem with microbore is if you move the water very quickly, it's very noisy, and the consumer, not surprisingly, won't put up with that. But one of my business partners lives in a house, pretty much the house I've been talking about. He has 10 mil microbore everywhere. He's had a heat pump in there for 11 years. Took a lot of balancing, a lot of clever maths and thinking, but we didn't change any of the pipework in the house at all, and it works perfectly on a heat pump. So you just need to be a little bit more cautious with microbore and check some figures. And we actually have a table we produce of how big a room can you serve with each size of pipework. Again, makes life nice and easy for installers before going to site and ripping the place to bits. So the last thing we need to check when we're on site, or the last two things we need to check, is we need to put a hot water cylinder in. Heat pumps are incapable of producing instantaneous hot water. There's all sorts of technical reasons why. So we tend to store a volume of water in what looks like a fairly standard hot water cylinder. But the only real difference between a heat pump cylinder and the cylinder you might have in your house is that we have a huge coil inside the cylinder to try and heat the water as quickly as possible. And the reason for this is it's not possible to heat the hot water and the house at the same time. So every minute spent heating your hot water is a minute that you're not heating the house. So if you do spend enormous amounts of time doing hot water, you have to oversize the heat pump to catch up on the heating. And that's not a particularly clever thing to do. So a sort of golden rule, if you will, is if you're having a heat pump put in your house, it is very, very likely that your cylinder will need to be changed. So that's something to bear in mind. We'll talk a little bit about radiators as we go through some case studies. So once that survey's come back, we pummel all the information into a calculator, and what we then do is compare your load with a heat pump, which will do the job, and a cylinder and the radiators and so on. And you end up with a pack of information which has a standard format. And the reason the format is standardized is if you want to get your RHI grant, there is a procedure that the MCS, they're kind of the police for the RHI, they make us go through a procedure to give all the information in a format that everyone can understand. So even though the homeowner may not want this information, they're always given it so that they're absolutely bulletproof. Everyone can see what's going on. And it's a really, really nice feature because it means that everything's done professionally and correctly. So I like to think that there are three types of retrofit. The first one we call the unicorn. So my house was a unicorn. Basically, it's an old house that's never been insulated. It's on single glazed windows. It's got no loft insulation, no wall insulation, no nothing. And these are fairly rare, as you can imagine now, but they're actually really easy to do, because what we do with the unicorns is we get the homeowner to put loft insulation, cavity wall insulation, and so on in, which massively reduces the heat loss of the building. What that means is that the existing heating system is now going to be too big for the job. And when we put a heat pump on it, it brings it back into size. So these are really, really easy to do. but unfortunately, like unicorns, you don't find them very much anymore. The vast majority of houses fall into what we call the normal sort of band. These are houses that were built in the past, in the 20s, 30s, whenever, but people have invested a little bit in insulation. They've put loft insulation in, they've done cavity wall and so on. They may even have had a new heating system in the last 15, 20 years. The problem with these houses is the heating system is already sized for the better insulated house. And so we might need to modify it a little bit to make it work really well with the heat pump. And I'll talk about that as we go through. And the last one are the big houses. So big, not necessarily in footprint, but big in heat loss. These ones can be very, very challenging to do. And if you are a heat pump denier, these are the houses that you focus on. So you'll see lots of people like the Sillet Bang Man doing videos about how it's going to cost £25,000 to put a heat pump into his house. I assume he's just doing better than I am and lives in a much, much bigger or much worse insulated house than mine. But it's very easy to go and find a house that is far too big to put a single heat pump in and use it as a ridiculous case study. But we will focus on, I have one just like this. I'll show you a bit later. So myth number one, heat pumps won't heat old houses. So I like to do a bit of myth busting. This house you see here is mine. This is our little house in Southampton. It is clearly old and quite peculiar, and I want to talk to you about it in some detail. So we bought this about 12 years ago, and it was a unicorn. It had no insulation. So it was 1922 construction. It had 100mm cavity walls, which we've now filled with blown rock wool, so you know the cavity wall insulation. We put double glazed UPVC windows in. Previously, it had single glazed windows. It's got wooden vented floors downstairs because it has open fireplaces. And just to keep the vent loss as high as possible, they vented the first floor as well because there are fireplaces in the bedroom. So ventilation loss is a major, major part of our heat loss in our house. The loft is open, so there's no felt, but we put 200mm of rock wool in. So bearing in mind my house is only 107 meters squared, my heat loss is 7 kilowatts now. Previous to us doing all of the insulation work, the heat loss was around 12 kilowatts. So we've dropped the demand of the building enormously. And you can see on the right here that despite all that work and all that lagging, we are now reaching a heady EPC of E. We were on G before. To move from E to C and B and A in a property of this age is really, really challenging to do and very expensive. And I'm going to leave that for others to discuss. But what is interesting when we look at our EPC, if you add these two figures together, we're running a heat loss in our house of about 12,000 kilowatt hours per annum to keep the place warm. Okay, so when we bought the house with this dreadful insulation, it also had an ancient gas boiler with a pilot light, and it also had what's called a single pipe heating system. So basically, they essentially had one pipe running all the way around the house. Now, these are very rare now. You don't see them. They were very popular in the 50s, but one of the advantages of the single pipe is in the rooms furthest from the boiler, they put lots and lots of big radiators. So when we came to put a heat pump in, we put the second pipe in, but we were actually able to use a lot of the radiators again. So these are the modifications that we had to do to our house. So we took out the existing boiler, which was running at something like 70 degrees C, and we put in our first heat pump, which was designed to run up to 55 degrees C. So the main differences we had were that the hot water cylinder, the one we had originally, was a little copper cylinder with a red duvet over the top. I'm sure some of you remember them from the bad old days. That was removed, and we put a new pressurized cylinder in with the much bigger coil. The radiators, normally we would have replaced them all as we renovated, but we were on a budget. So we actually left about 80% of them in there, because when we did our heat load calculation and worked out whether the radiators were big enough, we found they were. In a couple of the rooms, the capacity was a little bit low. What you've got to remember is if you drop a radiator from 70 to 55 degrees, it physically shrinks in size. About a third. So we needed to up the size of a couple of radiators in the house which were a little bit tight. So we were very lucky, basically, by increasing the insulation and then putting a lower temperature heating system in. We didn't have to do a massive amount of work. But this is quite peculiar. In a normal house, what you would find is it's very likely that a very large number of the radiators would either need swapping from room to room or replacing, because they're no longer big enough if you only run them at 55 degrees C. And this is where this myth of heat pumps are hard to do comes from. They are hard to do if you don't change the radiators, but if the radiators or the underfloor is correctly sized, you can run the system at whatever temperature you like. And in heat pumps, the colder you run the system, the better the efficiencies. Okay, the one thing that I would suggest if you're ever considering using an old system is flushing the system out. Those of you who've ever replaced an old radiator will know that when you tip them up, some hideous black liquid comes out, which ruins everything it touches, especially carpets. And you tend to get a bit of a roasting off your partner when you've ruined the lounge carpet with a big trail of black rust all over the place. So one of the things that we really push people to do when they're using old rads is really thoroughly flush all this old rubbish out of the system, make sure it's nice and clean. It also makes the radiators work considerably better when they're not full of old debris. But this is something every heating engineer on the planet knows how to do with a power flusher. So we have to be careful of a few bits and pieces, and one of the things that people say to you is that we're going to run this machine with a lower radiator temperature, and that's going to leave the house really cold. But bizarrely, that actually is the reverse of what's true. So my house has a very high heat load per meter squared. It's so bad, in fact, that if it's less than 15 degrees C outside, I have to turn the heating on. And it breaks my heart to tell you this, but last night we ran the heating in August because the house was cold. And it's just down to the fact that it is just appallingly built. So I'm running my system with a 15-degree ambient outside. So the efficiency of my heat pump is incredible. So yesterday I would have got a really huge coefficient of performance. It would have been even better if, of course, we'd had some insulation and the heating hadn't been on at all, but such is life. But one of the things that's kind of weird about this is if you have this high heat load and you have this problem that the temperature drops very quickly in the house, heat pumps love being run against this kind of system because their party piece is that they like to trickle heat into the house at a steady, constant amount, kind of drip feeding the house with heat. So what we do is we set it up with the thermostat that the unit's running on and on using weather compensation. We don't want to do an hour burst of heating and then turn it off for 4 hours. What we like to do is trickle the heat in and trickle the heat in all the time. So I always joke that my thermostat comes on in September and it goes off in April. And I have a system made by a company called Renewable Energy Devices, which is very sophisticated. And the designers at Renewable Energy Devices aim to make the system so perfectly balanced against the house that the heat pump starts 3 times a day. So it's on all the time. Unfortunately, I have to hold my hand up and say I've failed. My machine has started 1,329 times in 219 days, which is 6 starts a day. So people will say, well, you're supposed to be an expert. Why is your system not amazing? And the reason for this is one of comfort. So one of the things that you find if you set your weather compensation correctly is on a day like today where it's 15 degrees, I would probably want to run my radiators around about 25 degrees centigrade to maintain a perfect heat loss. But what we find, and my wife particularly complains about, is if the radiator is only 25 degrees C, it feels cold. So although it's heating, it doesn't feel like it's doing anything. And my wife likes to feel the warmth of a radiator. So we generally advise people, if you're interested more in comfort, never let the radiators fall below 37 degrees. The problem if you do that, of course, is that the machine cycles because you're emitting too much heat. So my machine is set up for the minimum radiator temperature of 37 so that we have, it feels comfortable. However, if I wanted to push for efficiency, I would drop that a little bit. And that's why at the moment I've only achieved a COP of sub 3. I get continually roasted by the guys at Red. who tell me that I need to adjust this because they want to see well above 3 in a house like mine. And this is an experiment I'm going to try, but it's a very difficult thing to convince my wife that the tepid radiators are heating the house enough. The room temperature in our house never drops below 21 degrees. It's rock steady, but people don't feel room temperature particularly well. They want to go and touch a rad and go, oh, that's lovely and hot. The heating's running. It's a challenge that we have in the heating industry. So I'm planning to tweak this, and I will bore you all with the end of year figures after Christmas. It's something to look forward to. So myth number 2 is heat pumps just won't give me the temperature I need. So this is another example, this house here. Bizarrely, this is one I know a lot about. I was born in this house. So I want to talk about this because this is one of those big houses which, if you're a heat pump denier, is a great one to talk about why heat pumps don't work. And I'll show you why. So this place was built in 1800. It has solid brick, single skin walls with no cavity. There's single glazed leaded windows. They put these in to make sure that the U value was enormous, so that we got a huge heat loss. The floor is solid dirt downstairs. The loft is completely open, and there is no insulation of any kind in there, and there's no access to the loft to get insulation in. The house is 200 meters squared, and the heat load is 22 kilowatts. That's 110 watts per meter squared, which is dreadful compared to a modern house. Just to add insult to injury, it's listed. So my parents pour 50,000 kilowatt hours of heat into this building per annum, using their gas boiler. And of course, they said to me, let's talk about a heat pump. But the graph you see over here on the right is the heat load of that building versus the output of the biggest heat pump that I know I can supply you. And you can see here that the lines crash, the red line being heat loss, the blue line being the output of the heat pump. And you can see that below about 3 degrees centigrade, that heat pump just is not going to maintain 21 degrees here in the house. So there you have it, graphical proof. It's impossible to heat that house with a single heat pump. And it's true. So what should you do? Well, in an ideal world, you go and buy a load of Celotex and insulate the house and so on, and bring that heat load down so that that one heat pump will do the job. But that is very, very difficult to do in a house unless you're renovating, because it's fairly major work. And bearing in mind it's listed, UPVC double glazing is not an option. So I want to look at how you would look at a house like this and see whether we could do something sensible which doesn't break the bank. But I like to use this example of some costs. So here we go. The house has got 22 radiators in, and I know from bitter experience that if they're not running at 70 degrees C when it's -2 outside, the place will be cold. So every single radiator in that house needs to be replaced. That's a cost of £4,400. We can't do this with one heat pump, so what we'd have to do is use 2 side by side. Some people call this cascading, which really winds me up. It's not cascading, it's 2 heat pumps. So basically you tube the 2 together. But the problem with this is if you have more than one heat pump in the garden, you have to get planning permission, and you won't get planning permission because it's listed. So that's not going to happen. But let's assume we have got planning permission. 2 heat pumps in. My parents annoyingly have a combi boiler, so they have no cylinder. So we need to build a cylinder cupboard and then put a cylinder in, which is going to cost another £1,500. We can't increase the insulation of the house easy because no one wants to do any renovation. So the total install cost of a new heat pump would be £25,000, which is crazy. The problem is also that the RHI grant is capped at about £11,000. So the payback is going to be forever. They're going to save something like £700–800 a year in run cost. Take the 11,000 off, it's going to take eons to pay this back. And as my dad loves to point out, he's 84, he's never going to see the benefit. So what do? Walk away and leave it, or do we come up with a solution? What is really interesting though now is the carbon saving on this building is over 10 tons per annum. So this is a really, really major driver, and people are looking at this going, yeah, I know it's expensive, but look how much carbon I'm saving. I'm really doing my bit. So it's a really interesting twist in the financials. So what I want to do is say, what would I recommend in a house like this? A lot of you are probably thinking gas boiler, it's the great future, but let's have a look. So there are a very few heat pumps out there on the market, which what I call ultra high temperature units. And this is an example of one. So essentially what we have here is a standard heat pump, which sits in the garden. You can see on the left. This connects into another heat pump, which is connected inside the house, which lifts the temperature from 50 degrees C up to a maximum of 80 degrees C. And this machine and these machines like simply designed to plonk in place of an oil boiler. So you take your oil boiler or gas boiler out, put this in its place and connect this to the existing pipework. So all of the pipework would stay in place, all of the radiators would stay in place, because I'm still going to run at 75 degrees C or 70 if we can get away with it. Now in my parents' house, what we would do is to save further money, we're going to leave the combi boiler in, and we're going to allow it to continue to make the hot water. The reason for doing this is it saves a lot of money, it saves a lot of messing around, but it also has another party piece. This machine is only going to be big enough on its own to heat the house to 21 degrees C if it's above 3 degrees outside. So below 3 degrees outside, I'm going to ask this boiler to come in and help, like a backup heater, and help the heat pump heat the house. So we call this a kind of backup solution, where both the heat pump and the boiler are going to run together. The boiler won't run very much, only about 10 or 15% of the time, but it's there if we need it, if we're pushing the heating system hard. So the thing that the installers like about this is a relatively easy installation, because you're not really messing around with the kit that's there. It has one other nice feature, which is this outdoor unit can be mounted up to 75 meters down the garden. So we can get it well away down the back of the garage, out of sight, so that the planners have no issue with putting this on the house. So this machine and ones like it were expressly designed for this kind of application. So if we now look at this insulation using this kind of insulation, first off, we don't need to replace the 22 radiators, so that will cost nothing. We don't need planning permission, and we're only going to have one heat pump, so the installation cost will be halved to about £10,000. The house is going to have a combi boiler in it. It's still there, so we're going to continue heating the water, so no hot water cylinder. And again, the grant will be capped around about the £11,000 mark. So in this case, the payback is much cheaper or quicker. Of course, the carbon saving is not quite as effective. You're not going to save 10 tons anymore. You're only going to save 7 or 8. But this is a really, really good first step towards getting these people away from 100% fossil fuel and at least doing part of the work with a renewable solution. So it is possible to do. It's slightly more challenging. You have to think about it a little bit more. It's just not just a plonk the unit on the floor and leave. You've got to think about this. And I always say to people, the key to a great heat pump system is to find a designer and an installer who work together and will provide you with a solution that will work. What I really mean by that is I see a lot of stuff on LinkedIn where manufacturers push and push and push a particular unit that they have in their arsenal. And I understand that they all have mortgages to pay and that's their job. But often it's the case that manufacturers have a very strong product line in one area and weak in others. And if you're unlucky, you might be choosing a machine which is not really the best you can buy. So it's always a good idea to try and get a little bit of independent advice from the manufacturer and say, what is the best machine for you? For example, you might think I want a Mitsubishi, but actually an LG might be better in that particular application, or a Daikin or whatever. So I think it's always a really good idea to shop around and find the best solution for you. If you go to someone who only has one brand, they are very limited by what they will do. So a bit of independent advice never really hurts. I wanted to really end this presentation talking about the future, and this is something that I have no crystal ball, but this is something which is causing a lot of discussion in our industry. We know, those of us who've been around a long time, we know the best solution is to try and sell you a system which is going to be massively high efficiency, low temperature, getting the very, very best out of your house. However, the cheap solution is to buy a unit which is basically a boiler replacement. And what you'll see now on the market is these machines are beginning to appear, which are simple, they're cheap, and they are designed to sit in the garden. So your plumber turns up, he chops the boiler off, he pushes the 2 tubes that went to the boiler out the wall and connects them to a heat pump, which is able to give you something of the order of 65 or 70 degrees C temperature all the time. Yes, I know the efficiency isn't going to be as good as it would be if you ran them at lower temperatures. But this brings a really, really interesting question, which I wanted to kind of end my presentation on, which is it better to get somebody to make the first step and move towards a renewable technology which isn't as efficient as it could be, instead of just getting them to get a gas boiler? And somebody from Bays said to me a really interesting point, which is, does efficiency matter as much if the energy that powers the machine is renewable? Surely getting them to do something renewable first and then working on the efficiency is an interesting idea. I don't know the answer to that. I'm sure there will be some discussion over the next few years, I'm sure, which really pretty much concludes my presentation and comes to the interesting bit, which is the questions.
Thanks, Graham. That was really interesting. Definitely makes me want to get a heat pump for my house. Okay, so let's go through some of the questions. So we've got one from Alex. As architects, can we engage with you directly, Graham, or do we need to come through as a subcontractor? What happens if the property isn't suitable for RHI, not suitable for cavity wall insulation, already has loft insulation? Is there any way to save on the cost of purchase?
So as far as the design is concerned, yes, you can come to me, and that's basically what I do for a living. So I would take the drawing from an architect, and I would come up with some kind of proposal. I'm sort of famous for the fact that I am one of the people who will tell you that, you know what, in this particular house, it may not be the way to go. I believe heat pumps work well in some houses and others they don't, and I'll tell you that. So that's kind of, yes, you can come to me, send me a drawing, I will do some simulation, like I showed. So we do it in 2 steps. The first step is free, of course, it only takes us a few minutes. If you need the full design and so on, we have to negotiate some kind of fee. So I do that with my company, and we would put that together. You can go to your installer for the same service, but what you tend to find as an architect, because you tend to be a little bit away from where the job is going to happen, it might not be happening for a year or so, the installers tend to want to work on projects where they're going to get an order fairly quickly. So people like I have the benefit of having a bit of time. The installer kind of wants to come round and have a look and see where everything's going to go, and that's more difficult to do off a plan. So yes, you can do that. As far as RHI is concerned, there is one golden rule: you don't get RHI for new build. And this isn't true, but I like this as a rule of thumb. If you choose to have a renewable technology in your house, you get a grant. If you buy a house where somebody else chose the renewable technology, you don't.
We've got another one, which is noise from heat pumps is something that planning is concerned about. What is your experience of this?
Okay, so we're very lucky. There is a simulation you have to do in MCS, which simulates the noise of the machine at the neighbour's house. So it's an established calculation that we use. Noise is a really, really key issue. Because the noise from a heat pump is very different from a noise from a boiler. So my next door neighbour has a gas boiler, it roars away, everybody accepts it. And when we're doing retrofit, and this sounds like an insane idea, but it actually works really well. If you're worried about the noise and you think the neighbours are going to complain, an air source heat pump sounds very, very like a microwave oven. similar level of noise, etc., droney noise and so on. So I actually get my customers to take the microwave outside, plonk it on the floor, plug it in with an extension lead and turn it on. And then go and have a mill around the garden, go in the bedroom, see what it sounds like. It's a really, really good way of kind of try before you buy, to see whether it's too noisy, because heat pumps do make a noise, and there are lots of idiots like me who put videos on YouTube saying, look at my silent unit, it's amazing. And you'll notice that all those videos are taken in the middle of summer when the unit's cruising gently along. Nobody's out there in November when it's frozen solid and flogging away. So I would suggest the microwave is a really, really good way of doing it. But they do make a noise. You can't put them in acoustic containers. It just doesn't work. You can hide them behind bushes and things, and that's what we find a lot of, is if your neighbor puts this big ugly white box in the back garden, you look out your bedroom window and you think that doesn't look great. We actually get people complaining before they're installed. And if you have a neighbor like this, let's get it hidden away, tuck it out of the way down by the wheelie bins. That's the best idea. But as a really, really rule of thumb, we would obviously calculate this for you. You need 7 meters from the front of the heat pump to the nearest openable window of the next door neighbor's house.
That's really interesting. Okay, we've got a few more coming in as well. Got one saying, we work a lot with Victorian terraces and would love to get the owners to go to the heat pump path. The space to locate an air source heat pump is always limited. Second, the noise issue. How are your experiences?
Terraces are tricky because, of course, by definition, you have very narrow plots. There are some very clever systems where you can mount the unit further away from the house, so that there are essentially 2 types of heat pumps. I won't bore you with the technology, but one of them lends itself to a long way down the garden, and one of them lends itself to very close to the house. So what we've tended to do with terraces in the past is use these systems with the pipework, run it down the garden wall and stick the unit out, kind of way down the garden is a good way to do it. There's so many different, to give you an example, we currently sell, I think, 400 different heat pumps. So to be able to remember them all is impossible. That's why you use people like us. There are systems where there's very little in the house, so it's nice and simple, kind of less hardware in the house. There are systems where there is lots of hardware in the house. So in smaller properties, terraced and so on, we tend to go for the machines where all the hardware, you have a bigger outdoor unit down the garden and less gear in the house. But yeah, terraces are a challenge because they tend to be very poorly insulated. But it's possible, anything's possible, we can work it out for you.
Cool, we've got one from Neil said, can a PV installation radically reduce running costs and RIO?
Okay, that's a really good question. So it depends how much of a shyster I'm feeling like at the moment. So if I look out the window today, it's beautifully sunny, my PV is pouring electricity into the grid, and I can tell all my friends that my heat pump is currently costing nothing to run. But it's August and the heating's off. And the problem is this, the output of PV is a sine wave and the output of a heat pump is a sine wave, and they are exactly out of phase with each other. So I always say to people, what is the contribution of your PV in the middle of November at night when the heat pump is working hardest? So we have done a lot of simulation on this, and actually what we find is you get about a 7% reduction in run cost with PV because what you get is your hot water for nothing during the summer months.
What if you added a battery in with your PV? Would that affect it?
I did once work out the size of a battery required to charge enough to drive the heat pump over the winter, and it is not a small battery.
Well, that sums it up for me. We've got another one coming in. I'm looking at a new build and considering locating an air source heat pump in a ventilated roof space. Have you any experience or comments on this idea?
If you want to do that, please don't buy the unit off me. it is an absolute disaster every time. Let me briefly explain. On a 16 kilowatt heat pump, it pushes 100 meters cubed of air per minute, through the unit. So to put that into context, if you put the heat pump in the front door of your house and turned it on, it would do one air change of your house in under a minute. So it doesn't matter how well vented that roof space is, it is going to freeze.
Okay. Yeah, so in the end, would it end up cooling the house as well?
Well, most importantly, you go in the loft to be minus 20 degrees C today. Your efficiency would be appalling. And the other problem is noise. So you get a lot of noise through the unit into the beams of the house. Please, I beg you, if you do anything, don't do that.
So we've got one more. Have you had to use loads of limiters a lot and or get the supply reinforced?
Can you say that? I didn't quite understand that one.
Have you had to use load limiters a lot and or get the supply reinforced?
Okay, I see what you mean. Yes. So what they're saying there is that you have a power supply, let's say of 32 amps. And if your heat pump is drawing too much current, you have to essentially throttle it back so that you're not drawing too much current. We have experienced this very rarely because we tend to only go for a single heat pump with a 32 amp supply. You've got to remember that the supply for my heat pump is the same as the supply for my kitchen hob. So it's not excessive. Of course, in the property I was showing you, my dad's house, if I had 2 units there, that's 64 amp supply. It's very rural. So you get all sorts of problems with your DNO application, your electrical application, and that tends to kill the job off. That's why we've developed these solutions which don't do this. So if you tend to pick that up when you're doing your electrical application. It's called a DNO. It's very, very boring, but the supplier would say to you, you cannot put that bigger machine in. But they are the sort of jobs where you tend to go, do you know what, maybe an electrical heating system isn't for you. If you've got supply problems, maybe you have to go for biomass.
Okay, that's really interesting. I think that's all the questions, unless... Okay, wait, we've got one more. Could you repeat the recommendations for pipe sizing, please?
Yes. So I have this tape. Basically, I'm a geek, and I like doing math or arithmetic. So what I worked out was how many kilowatts you can push down each size of pipe. And since I know how many watts per meter squared your house needs, I could tell you the size of room I could heat with each size of pipe.
Oh, right.
So it's a kind of reverse way of doing it. It's really good for the plumber. So he walks into your lounge, he says, you've got a 25 meter square lounge, you've got 8 mil pipe work, that's not going to be big enough. So it saves doing all the really tedious calculations. I do have this table, which I'm happy to share. I'm actually, annoyingly, that's my blog for this week on LinkedIn, so and on Mesh Energy. So it will be on LinkedIn this weekend. So I'd rather not spoil it today, but after Sunday you can have it. Where you tend to find that these ultra modern houses have a heat pump for heating and hot water and a totally separate air conditioning system for cooling.
Perfect. Well, I think you've answered everyone's questions, so we'll end the webinar there, but thank you so much, Graham. It was really interesting and very informative.
No, thanks to everyone for spending the time listening to me droning on.
It wasn't droning on. All right.
Thank you.
Thanks a lot. Thanks. Bye.